Hello everyone, hope all of you are safe. So today we will start part 3 of the solid state series and we will cover this topics, that is closed packed structures, tetrahedral and octahedral voids and stability of ionic solids in terms of radii of cations and anions. I hope you have seen part 1 and part 2 of the series. If not, you will get the link of those lectures in the description. So please follow those lectures before you see part 3. So without wasting time, let's start today's class. So we will start with close packed structures. Now we know in crystalline solids, the constituent particles, they are closely packed in space. These constituent particles are either atoms, molecules or ions which can be regarded as solid spheres. Now the spheres can be arranged in 1D, then in 2D and then in 3D so as to give you the space lattice. So let us find out how this mode of packing is actually done in 1D, 2D and 3D. To start with, close packing in 1D. Now in 1D, the spheres are arranged in a row like this. Now suppose we need to find the coordination number of this sphere, the sphere that I have marked here. So what is actually coordination number? Coordination number is the number of nearest neighbors in contact with a particle. So we can see there are two spheres which is in contact with this sphere, right? So we can say coordination number for close packing in 1D is 2. Next is close packing in 2D, that is packing in a layer. This can be done in two ways, square close packing and hexagonal close packing. So first we have square close packing. Now again we will arrange the spheres in a row just as in 1D. Now the spheres of the second row can sit exactly below the spheres of the first row like this. So here we can see that the spheres are aligned with the spheres of the first row. Again, the spheres of the third row can sit exactly below the spheres of the above two rows. So we get that rows have horizontal and vertical alignment, right? So suppose if we label the first row as type A, then the second row is also of the same type as that of first row. That is, it can also be labeled as type A. Again, the third row is same as that of the above two rows. So it is also of type A. So we can say square close packing is of AAA type. Now, if we need to find coordination number of suppose this sphere, right? Now this sphere is in contact with 4 spheres. So we can say coordination number for square close packing is 4. Next is hexagonal close packing. So again we will arrange the spheres in a row just as in 1D. Now the spheres of the second row can be placed in a staggered manner such that the spheres of the second row will sit in the depression of the spheres of the first row like this. So here you can see that the spheres are sitting in the depression of the spheres of the first row, right? So second row is different from the first row, correct? Now the third row will align with the spheres of the first row. So you can see that the spheres of the third row is actually in alignment with the spheres of the first row, correct? Now if we label the first row as type A, then definitely the second row is of a different type, that is type B. Now the spheres of the third row are in alignment with spheres of first row, that is it will be also of type A. So we can say hexagonal close packing is ABA type. Now if we find the coordination number for suppose this sphere. So we can see this sphere is actually in contact with 6 spheres. So we can say coordination number for hexagonal close packing is 6, right? So in hexagonal close packing, we can see that the spheres are much more closer to each other than in square close packing, because if we see the empty spaces in hexagonal close packing, you can see that the empty spaces are very much small, whereas in square close packing, the empty spaces are quite large. So here the spheres are closer to each other, right? Now closer the packing, greater will be the stability of the crystal. So we can say hexagonal close packing will be more efficient mode of packing than square close packing in 2D, right? Now coming to close packing in 3D, that is packing in space. So first is 3D close packing from 2D square close packing. Now in 2D square close packing, we have seen that the spheres of the second row are placed exactly below the spheres of the first row. So also the spheres of the following rows will be aligned with the spheres of the above rows. That is, they will have a arrangement of AAA type. Now the rows have horizontal and vertical alignment. Now if we add more layers, we will get this kind of arrangement, right? Now if we consider a cube, we can see that the spheres are present at the corners of the cube. So the lattice so formed is actually simple cubic lattice, right? Next is 3D close packing from 2D hexagonal close packing. Now we have seen in 2D hexagonal close packing that the spheres of first row are aligned in this manner, while the spheres of second row are arranged in a staggered manner, sitting at the depressions of the spheres of first row, and the spheres of third row are aligned with the spheres of first row. So in 2D hexagonal close packing, we can see some empty spaces. These empty spaces are called voids, which are triangular in shape, right? So we can see two types of voids. One is the red colored voids, that is the triangle pointing upwards, and the other is the green colored voids, that is triangle pointing downwards. Now we will form the second layer by covering the green colored voids. So I have shown the second layer by blue colored spheres. So you can see that I am covering the green colored voids one by one and forming the first row for the second layer. Now I will form the second row of the second layer by covering the green colored voids. So this is the second layer. Now coming to the formation of third layer. So third layer can be formed by two types. So first we will discuss type 1. Now in the second layer so formed, you can see two types of voids. One is the red colored voids that were already present in the first layer, and the other is the blue colored voids that are newly formed. Now the third layer can be formed by placing the spheres on this newly formed blue colored voids, right? So I am placing the spheres on the blue colored voids and forming the third layer. Now while I will be adding another sphere to this row, you can see that this sphere will actually align with the sphere of the first layer, right? Again you can see while I will be adding another sphere to the row of the third layer, it will also align with the sphere of the first layer. Correct? So we can say that the spheres of third layer are actually exactly above the spheres of first layer. So if we add another row of third layer, it will be exactly above the spheres of the first layer. Again, adding another row on the top, you can find they will also be aligned with the spheres of the first layer like this. Correct? So if we say that the first layer is of type A, then the second layer, which I have shown by blue spheres, which were formed by covering the green voids. Correct? They are of type B. Now the third layer, which was formed by covering the blue colored voids, were actually aligned with the spheres of first layer. So again, third layer is of type A. So arrangement is actually AB, AB, AB type. Okay. Now if I want to cut a portion of this arrangement, so I want to cut this portion of the arrangement so as to see how each layer looks like. So I have cut out this portion, and now let's find out how each layer looks like. So this is the third layer, right? This is the second layer beneath the third layer, and this is actually the first layer. So you can see that the third layer is aligned exactly above the first layer and is of the same type, that is type A. Correct? Now this was the view of the arrangement from top, right? That is, we were viewing the spheres from upwards. Now we want to view the arrangement from front. So how it will look like? So this is the first layer of type A, right? So the spheres that you can see here are actually these four spheres, and this one at the middle is actually this sphere. You cannot see these two spheres because they are at the back and you are viewing from the front, right? Now we will add the second layer of type B, which is formed by the blue spheres. Correct? Now we will form the third layer. So you can see it is exactly aligned above the first layer and is of the same type, that is type A. So we get AB, AB, AB type of arrangement. Now we want to calculate the coordination number. So this is the first layer, or we can say layer A, right? Now there is layer B beneath it and there is layer B above it. The arrangement is AB, AB type, right? So there will be layer B both above and below layer A. Now I want to find coordination number of, suppose, this sphere. That is the one I have marked. So this sphere is in contact with 12 spheres, as you can see. So we can say this type of arrangement, that is hexagonal close packing, has coordination number of 12, right? Now coming to formation of third layer by type 2. So let us form the first two layers in the same manner as we have formed in the previous slide. So this is the first row of the first layer. The second row is arranged in a staggered manner. The third row is in alignment with the first row, and the fourth row is in alignment with the second row. There are two types of voids. One is the red colored and the other is the green colored. The second layer is formed by covering the green colored voids shown by blue colored spheres. So you can see the second layer formation by covering the green colored voids, right? Now in the second layer we can see the red colored voids as well as the newly formed blue colored voids. So the third layer can also be formed by covering the red colored voids, this red voids. So here I have shown the formation of third layer by orange colored spheres, and these are covering the red colored voids, right? This is the first row of the third layer and this is the second row of the third layer, correct? So it is quite clear that the third layer is not in alignment with the second layer or the first layer. That is, third layer is different from first two layers. Now if I form the fourth layer by covering this blue colored voids, now you know that if I cover the blue colored voids, the fourth layer will be aligned above the spheres of the first layer, right? So I am covering the blue colored voids. Now as I will add another sphere, you can see it will align with the sphere of the first layer, right? Again the second row for the fourth layer, which will align with the spheres of the first layer. This is another row of the fourth layer, correct? So if I say that the first layer is of type A, second layer formed by the blue spheres by covering the green colored voids is of type B, third layer formed by the orange colored spheres by covering the red colored voids is of type C, and the fourth layer formed by covering the blue colored voids are actually aligning with the spheres of the first layer are of type A. So the arrangement is ABC ABC type. Now if I want to cut this portion of the arrangement, right? So I have cut this portion and separated out this portion, and now I want to see how each layer looks like. So this is the fourth layer, this is the third layer beneath the fourth layer, this is the second layer, and this is the first layer. So you can see that the fourth layer is aligned exactly above the first layer, and thus they are of the same type, that is type A. And the second layer and third layer, they are of exactly opposite arrangement, right? That is why they are of two different types. The second layer is of type B and the third layer is of type C, right? Now this was the top view of the arrangement. Now if I want to view the arrangement from the front, so this is the first layer of type A, right? Now I will add the second layer of type B. So the spheres that you can see are these two spheres. This sphere is at the back, so you cannot see while you are viewing from the front, right? Now adding the third layer of type C, and finally the fourth layer, which will align with the spheres of the first layer, that is of type A. So we'll get ABC ABC type of arrangement, correct? Coming to coordination number. So this is the layer A, right? Now we know we have layer B above layer A, right? And beneath layer A we have layer C. Since the arrangement is ABC ABC type, Correct? Now if I want to find the coordination number of this sphere, the one that I have marked. So let us find out how many spheres are in contact with this sphere. So we can see that 12 spheres are in contact with this sphere, right? So this type of arrangement, which is known as cubic closed packing, has coordination number of 12, right? Now coming to why cubic closed pack structure is also called face-centered cubic. So this is the front view of the CCP structure. Now here I have shown the fourth layer of the CCP structure. So I will remove all the spheres except the sphere at the center. This is the third layer. I will add one row to the third layer. This is the second layer. I will add one row to the second layer also. And this is the first layer. Now again I will remove all the spheres except the sphere at the center. Let this be the axis. Now I have redrawn the structure here, just that here the spheres are a bit spreaded out. Okay, this is the axis. Now if we join the spheres, we can see a cube at the background. Now if we rotate along this axis by 45 degree, the cube at the background will become like this. After rotation, the axis after rotation will go at this position. And now let's find out where the spheres will go after rotation. So for the fourth layer, the sphere will occupy one corner. For the third layer, the sphere of the first row will occupy one corner. For the sphere of the second row, one sphere will occupy the center of the ceiling. Another sphere will occupy the center of the right side wall. For the third row, one sphere will go at one corner, another sphere will go at another corner, and the third sphere will be present at the center of the back wall. Correct? Now coming to the second layer. For the first row, the sphere will go at one corner. For the second row, one sphere is present at the center of the left side wall. Another sphere is present at the center of the floor. For the third row, one sphere will go at one corner, the other sphere will go at another corner, and the third sphere will be present at the center of the front wall. Right? And for the first layer, the sphere is present at the corner like this. Now this structure is actually the FCC structure, and that's why CCP is also called FCC, right? So the next topic is voids or interstitial sites. So in closed pack structures, you have seen some empty spaces between the spheres. These empty spaces are called void, hole, or interstice. Now these voids are of two types, tetrahedral voids and octahedral voids. So first we will study about tetrahedral voids. So tetrahedral voids are formed when a triangular void formed by three spheres comes in contact with another sphere either from above or from below. So these are the three spheres forming a triangular void. Now if we add one sphere from the top and cover the triangular void, then the void that will be generated by covering the triangular void with a sphere from the top will be tetrahedral void. So now I am adding a sphere from the top, and hence I have covered the triangular void. Now if I fade out this sphere from the top that I have added, then we can actually see the formation of the tetrahedral void due to covering the triangular void with a sphere from the top. Now if we view it from the front, then we can see three spheres forming the triangular void. Now again, while we will add one sphere from the top covering this triangular void, the tetrahedral void would be formed, right? we can also say that a tetrahedral void is formed when four spheres placed at corners of tetrahedron touch each other. Now if we rotate these four spheres in this manner, and if we join the centers of these four spheres, then we can see formation of a tetrahedron, right? So we can also see that if at the corners of tetrahedron four spheres are present and if they are touching each other, then a tetrahedral void would be formed, right? So the arrangement of spheres around the void is tetrahedral. Coming to characteristics of tetrahedral void. Size of the void is much smaller than the size of the sphere forming the void. And if the size of the sphere is large, that means size of the void would also be large. Coordination number of tetrahedral void is 4 because 4 spheres are forming the tetrahedral void. Tetrahedral void means that 4 spheres are forming the void when they are arranged in a tetrahedral manner, right? The radius of tetrahedral void is 0.225 as compared to the sphere forming the arrangement, and we will calculate the value of this radius in the next slide. Coming to the calculation of radius of tetrahedral void. So let us consider a simple cubic cell which have 8 points or 8 spheres present at the corners of the cube. Now a tetrahedral void will be formed when 4 spheres are present at alternate corners of the cube. So if we fade out some of the spheres, you can see now that there are 4 spheres which are present at alternate corners of the cube, right? And if we join the centers of all these 4 spheres, you can actually see formation of tetrahedron. And we know that if the spheres are arranged tetrahedrali, they will form a tetrahedral void like this, right? Now all the spheres are touching each other, but for the sake of convenience I have not shown them that they are in contact with each other, but you need to remember that all the spheres are actually touching each other. The radius of the tetrahedral void is small r and the radius of the sphere is capital R. The edge length of the cube is A. Okay. Now if we consider the right hand triangle ABC. So this is the triangle ABC. Now if we apply Pythagoras theorem, we can write AB square is equal to AC square plus BC square, right? Where AB is actually the face diagonal, correct? Now AC and BC are actually the edges which will be equal to A, right? So we can write AB square is equal to A square plus A square, or AB is equal to A root 2. Now we know that the spheres touch each other like this, correct? So AB, that is the face diagonal, have 2 spheres that are touching each other. So AB can be written as 2R, right? Now if we put the value of AB, that is A root 2 here, we can write A root 2 is equals to 2R, or R can be written as A root 2 by 2 or A by root 2, which is the equation 1. Now let us consider the right hand triangle ABD. So this is the triangle ABD. Now again apply Pythagoras theorem. We can write BD square is equal to AB square plus AD square, correct? Where BD is actually the body diagonal, right? Now in place of AB, we can write A root 2 and AD is again the edge. So we can write A here. So BD would be equal to root under A root 2 whole square plus A square, which will be equal to root 3A, right? Now again the spheres touch each other like this. So BD is the body diagonal. Now at point B, there is a sphere. At point D, there is also a sphere, because we know in SCC, all the 8 corners have one sphere, right? But here, for the sake of simplicity, we have shown only the 4 spheres which are forming the tetrahedral voids. But at point D, there is actually one sphere that is present, right? So R are the radius of the spheres, and the tetrahedral void is located at the center of the body diagonal, whose radius is small r, correct? So we can write BD is equals to 2r plus 2 small r. Now if we put the value of BD, that is root 3a, in this equation, it will be equal to root 3a equals to 2r plus 2 small r, right? Or we can write r plus small r equal to root 3a by 2. So this is the equation 2, right? So this is the equation 1 and 2 from the previous slide. Now on dividing equation 2 by equation 1, we will get r plus small r by r is equals to root 3a by 2 into root 2 by a, right? Or we can write 1 plus small r by r is equals to root 3 by root 2. Or small r by r is equals to root 3 by root 2 minus 1. And if we calculate this value, it will come out to be 0.225. So radius of tetrahedral void is 0.225 as compared to that of the sphere. So the next type of void that we will study is octahedral voids. Now octahedral voids are formed when 3 spheres that are arranged at corners of an equilateral triangle is placed over another set of 3 spheres that are pointing in opposite direction. So this is a set of 3 spheres, and you can see they are pointing in upward direction. So the another set of 3 spheres that we will be placing over these 3 spheres must point in opposite direction. That is, they must point in downward side, right? So now I will be adding 3 spheres, and you can see that they are pointing in the downward direction. So the void that is being formed is actually the octahedral void. Now if we view it from front, we can see 3 spheres that are pointing inwards. So while we will be adding another 3 spheres from the top, they must point outwards in the opposite direction, right? So the void that is being formed is actually the octahedral void. Now octahedral void is the empty space that is formed at center of 6 spheres when they are arranged octahedrali. Now if we join the center of this 6 spheres, we can actually see formation of an octahedron. So these 4 spheres are present at plane of octahedron. This sphere is present above the plane of octahedron, and this sphere is present below the plane of octahedron. We can also say that if at the corners of octahedron 6 spheres are present and are touching each other, then an octahedral void will be formed, right? Now coming to characteristics of octahedral voids. So the size of the void is much smaller than the size of the sphere, right? Coordination number of octahedral void is 6 because 6 spheres are forming the octahedral void. Radius of octahedral void is 0.414, which we will calculate in the coming slide. So now we will calculate the radius of octahedral void. So let us consider an octahedron, and 6 spheres are present at 6 corners of the octahedron. This 4 spheres lies on the plane of octahedron. This sphere lies above the plane, and this sphere lies below the plane. Now we know that if 6 spheres are located at corners of an octahedron, they will form an octahedral void like this, Now here we will consider only the cross section or the plane of the octahedron, which is actually a square. So let us fade out the spheres that are present above and below the plane. Now the length of each side of square is a, right? Radius of the octahedral void is small r and radius of the sphere is capital R. Now let us consider the right-angled triangle ABC. Now if we apply Pythagoras theorem, we can write AC square is equal to AB square plus BC square, right? Now we know AB and BC are the sides of the square and they would be equal to A. So we can write AC square is equals to A square plus A square, or AC would be equal to A root 2. Now here I have shown the triangle ABC. Now if we look at the diagonal AC, we can see that at points A and C, two spheres are present, and also the octahedral void is located at the center, whose diameter is equal to 2 small r. So we can write AC is equals to 2r plus 2 small r. Now if we put the value of AC, A root 2 in this equation, we will get A root 2 is equals to 2r plus 2 small r. This is the equation 1. Also, AB is equals to 2r because at points A and B, two spheres whose radiuses r are present. Now AB is also the side of the square whose value is equal to A, right? So we can write A is equals to 2r. So this is the equation 2. Now if we divide equation 1 by equation 2, we will get A root 2 by A is equals to 2r plus 2 small r by 2r. Or we can write root 2 is equals to r plus small r by r. Or we can write 1 plus small r by r is equals to root 2. This can be written in this manner. Small r by r is equals to root 2 minus 1. Now if we calculate this value, we will get 0.414. So the radius of octahedral void is 0.414 r. That is, the radius of octahedral void is 0.414 as compared to that of the radius of the sphere, right? Next is locating tetrahedral and octahedral voids. So we have this generalized formula which says that if there are n spheres or n constituting particles, the number of octahedral voids would be equal to n and number of tetrahedral voids would be equal to 2n. So if we consider FCC, that is face centered cubic cell, we know they have 4 atoms per unit cell. So number of octahedral voids would be equal to 4 and number of tetrahedral voids would be equal to 2 into 4, that is equal to 8. So now we will try to locate this 4 octahedral voids and 8 tetrahedral voids in FCC. So let us locate the octahedral voids in FCC. So one octahedral void is present at body center of the cube. Now if you remember that in FCC there are 8 points at 8 corners of the cube, and then there are 6 points at the center of 6 faces, right? Which together looks like this. So these are the 6 points at the center of 6 faces. Now if we join these points like this, you can actually see a formation of an octahedron. This 4 points lies on the plane of octahedron. This point is above the plane and this point is below the plane. So at the center there will be a formation of an octahedral void, right? Now each edge has one octahedral void. So again we will consider an unit cell. So let us consider these 2 points at the corners. Now this point is present at the center of the back wall. This point is present at the center of the back wall of this unit cell. this point is actually present at the center of the side wall, which is shared by these two unit cells, and this point is present at the center of the side wall of this unit cell. Now if I paid out these two unit cells and join these points, now you can see a formation of an octahedron, right? Thus at the center there will be formation of an octahedral void. Now we know there are 12 edges in a unit cell. So in all the edges there will be one octahedral void at the center, like this. So there will be 12 octahedral voids at the centers of 12 edges, right? Now each void at edge is shared by 4 unit cells. So you can see this void at the edge is shared by this 4 unit cells. So we can say contribution of void at edges per unit cell is 1/4. Now if we calculate total octahedral voids in FCC, it would be equal to 1 plus the 12 voids at the center of the edges whose contribution is 1/4, that is 12 into 1/4. So this would be equal to 1 plus 3. So total octahedral voids in FCC would be equal to 4, right? Now let us locate tetrahedral voids in FCC. So there are 2 tetrahedral voids located on each body diagonal. So if we consider these 4 points, this point is present at one corner, this point is present at the center of the ceiling, this point at the center of the side wall, and this point at the center of the front wall. Now if we connect these 4 points, we can see formation of a tetrahedron. Now we know that if 4 points are located at corners of a tetrahedral void will be formed like this. So this tetrahedral void is located on a body diagonal, and we know in each body diagonal there will be 2 tetrahedral voids. So at the other end of the body diagonal there will be another tetrahedral void, right? Now there are 4 body diagonals in a unit cell, like this. We can see the 4 body diagonals. Now in this body diagonal there are 2 tetrahedral voids, one that I have shown here, this one, and the other one, as I said, will be on the other end of the body diagonal. So in the similar manner, in the remaining body diagonals there will be 2 tetrahedral voids each. So in the 4 body diagonals there will be in total 8 tetrahedral voids, which are not shared by any other unit cell. Thus its contribution will be 1. So in total there will be 8 tetrahedral voids in FCC. Thus total voids in FCC is equal to 4 for octahedral voids and 8 for tetrahedral voids, that is 12. Now in the generalized equation we have seen that if there are n spheres, there will be an octahedral voids and 2 tetrahedral voids. So we can say if there is one sphere, there will be one octahedral void and 2 tetrahedral voids. Thus we can say there is one octahedral void per sphere and 2 tetrahedral voids per sphere, right? So few slides back we were forming the structures of CCP and HCP in 3-dimensional. So let's form that again. So this is the first row of the first layer. This was the second row arranged in a staggered manner. And this is the third row aligned with the first row. There were 2 types of voids, the red colored voids and the green colored voids. So while we were forming the second layer, we were covering the green colored voids by adding a sphere above it, right? Now, if you look carefully, these are actually the triangular voids formed by 3 spheres. And now if we add a sphere from the top, then a tetrahedral void would be formed, because we know when a triangular void is covered by a sphere from the top or below, a tetrahedral void is formed. So now I will be adding a sphere from the top to form the second layer, like this. So now we can say that the triangular void is covered by a sphere from the top. So a tetrahedral void is formed. So in each cases, a tetrahedral void is formed as spheres are covering the triangular voids from the top, right? Now after the formation of the second layer, you can see the red colored voids that were actually present in the first layer. This red colored voids are now the octahedral voids. So we have studied that an octahedral void is formed when a set of three spheres that are arranged at corners of an equilateral triangle and another set of three spheres that are aligned in opposite direction is placed above the first set. Then at the center an octahedral void is formed. Now if you look carefully, the orientation of these three spheres is like this, and the orientation of the spheres of the first layer is like this. So we can say at the center the octahedral void is formed, right? Now I will fade out the first row so that we can see the formation of tetrahedral voids. So now we can say this green colored triangular voids, which is now covered by the blue colored spheres, has formed the tetrahedral voids, right? So the next topic is stability of ionic solids in terms of radii of cations and anions. So in ionic crystalline solids, the anions participate in the closed packed arrangement. That is, in the closed packed arrangement, the spheres will be anions in case of ionic crystalline solids, and the cations will occupy the empty spaces, that is the voids. Now for stability of ionic crystal, the electrostatic force of attraction between cations and anions must be maximum. This will be possible when cations are touching maximum number of anions and vice versa, and this will depend on the size or radius of cation and radius of anion, right? So this is expressed in terms of radius ratio, which is equal to radius of cation denoted by R plus by radius of anion denoted by R minus. Now for cations to occupy tetrahedral voids, this should be the condition. Now we know that radius of tetrahedral void is equal to 0.225 R, right? Now in this case the cations occupy the tetrahedral voids, so the radius of the cation must be equal to the radius of the tetrahedral void, and the anions form the closed packed arrangement, so the radius of the anion must be equal to the radius of the sphere. So this equation can be written in this manner, that is R plus is equal to 0.225 R minus, right? Or the radius ratio R plus by R minus is equal to 0.225 for cations occupying tetrahedral voids, right? Similarly, for cations occupying octahedral voids, we can write R plus is equals to 0.414 R minus, or R plus by R minus is equals to 0.414. So for a cation to occupy the tetrahedral void, the minimum value of radius ratio must be 0.225, and for a cation to occupy octahedral void, the limiting value of radius ratio must be 0.414. So we can say that for tetrahedral coordination, which is equal to 4, the radius ratio value must lie in the range 0.225 to 0.414, right? So for cations to occupy octahedral void whose coordination number is 6, the radius ratio must lie in the range 0.414 to 0.732. And if the radius ratio value lies in this range, then the cation occupies cubic void whose coordination number is 8. Now here I have shown the formation of a cubic void. So this is a simple cubic cell where 8 points are occupying the 8 corners. So at the center, a cubic void will be formed like this. And the coordination number of the cubic void is 8, since 8 spheres are forming the cubic void. Now if radius ratio lies below 0.225, then cation will occupy triangular void whose coordination number is 3. So this is the table which describes the relation in radius ratio and coordination number. So if the radius ratio value lies in this range, coordination would be 3 and arrangement would be trigonal planar. If the radius ratio value lies in this range, coordination would be 4, arrangement would be tetrahedral. If the radius ratio value is this, then coordination would be 6 and arrangement would be octahedral. And if radius ratio value lies in this range, then coordination would be 8 and arrangement would be cubic. Now, where from this radius ratio values are derived, this part is not included in your syllabus, that is the syllabus for 12th, and neither it is included in JEE or NEET. So we will not describe in detail that from where the values of radius ratio is actually derived, but I thought to make a separate video about this where we will derive the values for radius ratio, so that if anyone is interested and wants to know more, can refer to it. So with this, we have come to the end of our today's lecture. Here I have mentioned the topics that we will cover in our next lecture, and you will get the PDF link of today's lecture in the description. So if you have liked the video, then don't forget to like, share and subscribe to the channel. Thank you.